that. What do you think would be true about 6 heads versus 8 heads? Think about it for a second. How should those probabilities be related? They're probably getting 6 heads, which means I get how many tails? I like it. 8? Be less specific. And if I get 8 heads, I get how many tails? 6. Can you realize, if I figured this probability out, do I have to do any work for this one? Well, how should these be related? They should be the same, shouldn't they? Getting 6 heads or getting 8 heads, getting 6 heads means getting 8 tails. So the probably getting 8 heads should be equal to the probably getting 8 tails. Think about it for a second. Because they're equally likely, right? So how would you get the probability X is 6? Yeah, 14. Choose 6.
0.5, 0.5, 8.
And so somebody, you realize that's still 0.5 to the 14, right? It's always going to be that. So what's that? Help me out.
What is 1832 or 1833?
Do it again, sorry. 1833. So this would also be 1833. All right, I like it. I like it. So let me see if I can't speed this along a little bit. Let me show you something kind of cool. It's from the old book, but I don't care. We'll take a look at it. It's in here. I don't think so. That's neat. It says one thing and it's doing another thing. There we go. Alright. That's not what I want to show you. That's not what I want to show you. Quick way to do this. Let me see. Here we go. Cool. Ooh, it's gross looking. Sorry. I always say that when we get somewhere. Alright, let me just use. That looks nice. That's normal. I don't want that. That's the T. I don't want that. Binomial probability. Here we go. Alright, I'll use this. It looks disgusting. That's right. So now. A binomial table, all it does, and of course they don't have 14. Why would they? No, I don't want that. Oh, well, there's no quick way to get it. Okay. Advertisement, no. All right. Have 14, have 14. Yes, you do. Okay, good. All right. Now it's exciting. Okay, so real quick. So here's like the probabilities. And see how n is 14, and this is the number of successes. So if I have 14 total, how many successes could I have? Anywhere from 0 to 14. So does everybody see how to read this? Now watch. What's the probability of success for us? Flipping this coin. Probability of success is 0.5. Right? 50% chance I'm going to get ahead when I flip a coin. So I'm going to be in this middle column here, right? 50% chance. Right? The heading for this is way up there, so too bad. What did we already figure out? Did we do probability x equals 7? Probability x equals 7 was what? 2095, right? So let me see where am I? 5 is here. There. I'm going to let you absorb that for a second. You guys see that? So all this is a quick summary of all the possible probabilities. That's what a binomial distribution table is. And then didn't we do the ones around it? 0.183?
Yeah.
Right? Okay, cool. So, even though it took a while to find the damn thing, this is supposed to make this quicker. So we didn't have to use that formula for everybody. Can somebody tell me, you should have already gotten this from what I was saying, but what's happening if I drew this histogram, what would it look like? Yeah, so everybody at home, we're looking at that. Okay. If I drew this histogram, the tallest bar would, of course, be where? 7. So I have like this here. And it would go up to about 21%, right? So we'll just say 0.20 here. So it's about 21%, just above that. How we go so far? And then 6 and 8. Now notice how I drew this. Ooh, right? It represents 7, but I pretend like I had some width to it. Right? It still means 7. There's no way I can have... But what does this bar go from to? If that's 6 and that's 8, what officially does that bar kind of go from to? Yeah, from 6.5 to 7.5, right? I made that a little too far away. And then the next column would be about to 18, right? What is 18? My scale sucks, but too bad. So for this, from 6 to 8, and so forth. So, if probabilities are areas, and they are, it makes sense if I draw it like this because this is 1 wide times how tall it is the probability of that thing. Are you guys kind of with me here? So if I draw my histogram correctly for binomial, it's still the areas. It's discrete because it's not really, there really is a big gap between 7 and 8. Right? So this is discrete because it goes 7, 8, 9. Okay. So what's going to become important towards the end of this next chapter is I'm going to come back to this. I actually have a little handout that has this on it. And I'm going to make the connection between pretending like this is continuous. So if I kept going, what do you think this picture is going to look like? And the next one goes up to, where'd it go? 12. I like it, 12. And then 6. And then so forth. So what does that look like? What shape is that? Bell curve. It's normal curve. It's very close to a normal curve. And I knew it was going to be symmetric because P is 0.5. Think about it. If P is 0.5, it's going to be symmetric like this. You guys kind of with me? In fact, if you look at 15.5, it's symmetric in a slightly different way. If I had flipped it 15 times, what's the highest bar going to be? 7 and 8. Why does it make sense? What's half of 15? 7.5. So expect 7.5. What the hell does that mean? 7 and 8, they're both the highest. That's why I expect 7.5, because I'm splitting the difference between the two things that's going to happen most likely. Okay, maybe. But it's still symmetric. As you go out from there, where'd it go? Here it is. So as you go out from there, they go equally down on both sides, so it would still look normal. So what we're going to do later this semester is we're going to talk about when can I say something is normal enough. Because what's so nice about being normal is empirical rule is a lot more specific than Chebyshev's rule. So if I know it's normal, I'm going to know a lot about the probabilities. I'm going to have this whole table of values for the probabilities. So what if I said, what's the probability it's 6, 7, or 8? What would I do? What would you do with each of those probabilities? Okay. It's almost done. 6, 7, or 8. Or means add. So I would just take the probability 6 plus probability 7 plus probability 8. That would be the total area from 6 bar to 8 bar. How are we doing so far? Is that cool?
Yeah.
I like it. So the connection I want to make is this next chapter, chapter 6, is all about the normal curve. And this is the most important section in the book, the most important chapter. Right? It's going to set up everything basically for the rest of the semester. So I can't make that any more clear how important it is. We're going to start doing stuff like this. So I already know, for example, can you guys help me out? What percentage is below there for a normal curve? Somebody remember how to figure that out? What's between 1 and -1? How much is there? Empirical rule. How much says within 1 standard deviation there's what percent? 68. So between there's 68, which means how much is outside? 32, which means how much is just below -1? So the probability that a z-score is less than -1. The probability that I am more than 1 standard deviation below the mean. Is that cool? You guys get that? Because what does the z-score mean? What does z-score tell you? The number of standard deviations away from me. So this question is, what's the probability that your data point is more than 1 standard deviation below the mean? That's what they're saying. And we know that that's going to be about 16%, right? Because outside is 32, so on this side there is 16%. Stay with me now. Stay with me. So here's the chart we're going to use. Oh, God, Jeff. Oh, God. See how long it takes you to find this. No, this will take me just a second. So here's this chart. This is the last thing we're going to talk about today. Whoa. Okay. Here it is. Z-scores. So I just want to show you very quickly how this chart still contains empirical rule. It has to. But this is like empirical rule on steroids. It's not just 1, 2, 3. It's 1.12 and so forth. So if I wanted to know, so look, what does this chart tell me? If I look up a z-score, it will tell me the area below that z-score. Do you see the picture tells you what the hell the chart's telling you? So if I look up a z-score of -1, it'll tell me the area below -1, and areas equal probabilities. So if I look up negative, now look at, this is very weird how they set this up. If I want -1, it's -1.00. So I look at -1.00. So if I wanted -1.02, I would look at -1.0, and then I would go over to this column. This is 0.02 here. If I wanted -2.93, I'll go -2.93. So that much area is below -2.93. So what area is below -1? 1587, which rounds to 16 frickin' percent. Shit. So this chart is what we're going to get into next time. We're going to do several examples of how the hell to use this chart. All right. Thank you.